A function has a local extremum at a point where it takes on the largest or smallest value in a region around that point. Global extrema are the largest or smallest values of the function anywhere on the domain. Below is pictured the function f of x comma y equals x squared plus y squared. From the graph, we can see that it apparently has a relative min at 0, 0, the origin, and that also happens to be the absolute min of the entire function. So for this function, can we find output values f for different combinations of x and y? It's something that you may be able to just do in your head. Go through each combination of x and y and just square those and then add the results. Alright, the table is complete. According to this table, what is the minimum value of the function? Well, so far all evidence points to 0 being the minimum of the function. It apparently occurs at an x of 0 and a y of 0, so it's at the origin. As a coordinate pair, the minimum occurs at 0, 0. But so far we haven't proven that that's the actual location of the minimum. And proving the location of the minimum is part of the topic of this section. So what are the conditions for having a local max or local min in a two-variable function? For a one-variable function to have a minimum or a maximum, we would need the derivative to be 0. Since this is a two-variable function, though, we actually need both the partial derivatives to be 0. If both partials are equal to 0, then there would exist a tangent plane. The tangent plane is drawn here on a couple different surfaces, and it's similar to a tangent line except that it's a two-dimensional object. And it will brush up against the curve at a point such that the slopes of the plane match the slopes of the surface. So for the function f of x comma y equals x squared plus y squared, we need to first find the partial derivatives. Fx is going to be 2x, and then we'll see that fy is 2y. And we're going to need to set both the partials equal to 0. Just like we would in single variable calculus. Now we have to solve those equations simultaneously and interpret the results. We get 0 equals x and 0 equals y. And so there's only one location where the tangent plane will be horizontal. The solution is 0, 0, just as we had found in the table.